I would like to thank the SPE Student Chapter of UTT through Mr. Dacey in facilitating this October Tech Talk on laser scanning and evolving construction. So let me see if I could try to share my screen. They might need to give me permission to do so.
Yes, I think we're good there now.
Okay, let me check it. Everyone seeing it now?
Yes, we're seeing
Yes.
it.
Okay, great. Okay, so we're going to speak today about laser scanner within the construction industry, and we say evolving construction industry because it's an industry that's developing very slowly. Actually, when you compare to the industries like automotive and also the manufacturing, it's not 100% automated. It's really lagging behind. So until construction becomes automated, we'll have the challenges in managing all the different disciplines involved in a construction project. One of the biggest challenges being the management of human capital. And BIM, which stands for Building Information Modeling, will be one of those such processes which would aid in the 3D scanning to address this major challenge. So we're going to go into the other slide here now. We just have like about 20 slides, and we have like about 3 or 4 short videos. And also we will look at some live data that I have prepared in the background. All right, so that's just the quick course outline. We're going to speak about L&S Surveying Services, what we do, who we are, what is 3D laser scanning, the data workflow, what the scanner could do, some of the applications. We're going to speak about BIM, look at some sample projects, and as I said before, look at some live data that we have on the background there, and then close off with the benefits of the laser scanning. So, catchphrase today, if you can see it, you can scan it. So about L&S Surveying Services, you can see our clientele. This is a snapshot of, I would say, like about probably 10 or 15% of our clients. And if you look at it, most of them are heavily involved in the energy industry. Okay, so you can see like the upstream people like Shell, Atlantic, BPTT, right, NGC, BHP Billington. And then we have some of the major engineering firms like Massey, Worley, Fluor, right? So L&S Surveying started quite in 2000, and it established itself as one of the leading surveying companies, right? We have approximately 50 employees. And if you look at the picture of our building there, we have 3 main floors. The first floor is dedicated for surveying alone. The second floor is for the drafting department and QAQC. And the third floor deals with the admin and accounting. And as I said before, most of our projects are really in the engineering field. I think probably 80 to 85% of our revenue comes from the energy industry. So we do laser scan surveys, as you should guess that. Underground detection protection, which is whereby we're using equipment like the ground probing radar and a pipeline locator to find underground features, and UAV mapping. Now, these 3 services are what we call our advanced services. And these are the services we think that set ourselves apart from the competition, because not many surveyors have these 3 pieces of services within their arsenal. Some may have 1, others may probably have 2, but not all 3 of them. Then we have normal topographic surveys, which most surveyors would do, hydrographic surveys, surveys on the sea, GIS, drafting services, and cadastral surveys or boundary surveys whereby people establish legal limits for their land. So that's a snapshot of L&S Surveying Services. So what is laser scanning? So I tell my students, we need to look for 4 keywords. And the keywords are automated, rapid, reflectorless laser. And you can pull those 4 words out alone and use it. Right, so I have here an automated, rapid, reflectorless method by which measurements are obtained to recreate the environment by the use of a laser. So people who are familiar with surveying, you could have an actual total station that takes prism-less shots with a laser, but it's not a laser scanner because it's not rapid, and some are not automated. We do have total stations which are automated, right? Reflectorless shots with a laser, but not rapid enough. And rapid is when we're speaking about points that reach tens of thousands of points per second it could capture. So laser scanners are grouped basically in two categories: time of flight, as you should know. Basically, it gets the distance ranging from measuring the time, the speed of light, and the other one uses a phase shift. And quite back in the mid-80s, the first reflectorless distance meter was developed. And only till the late 90s, it had the first laser scanner. You see there, it was big, bulky, ugly, heavy, right? And it did only 1,000 points per second. Around early 2000s, we had the first set of phase-based scanners. As you can see, it's much smaller, a lot of cables still hanging out. And you're realizing that some geologists more using the technology, because back then there were no photos. You just get millions and millions of points. And when you zoom in, you can't recognize anything. You had to zoom out. Then we start getting to more modern day type scanners. Around 2007, Topcon had this laser scanner. They did 30,000 points per second, had onboard data storage, and it had about a 4mm accuracy in picking up data. Fast forward to 2014, you have laser scanners do almost 1 million points per second. It's much more compact. Now that Topcon you see to the left it's kind of bulky. It weighs like almost 30 pounds compared to the Pharos to the right, which would be about 17 pounds itself. And you can see it's remote control. So it has a LAN address. You could actually take your phone and go remotely and control the laser scanner. And you have integrated GPS, and you can see the accuracy has increased to about 2 millimeters ranging distance. And then now, 2018, we have 1mm accuracy, nice feature, side calibration feature, have HDR overlay, which is high dynamic range, whereby photos are taken at different ISO values and overlaid to get a nice rich photo. And 2019, we've seen Leica, they're coming out with a similar type equipment, but of course, it's 2 million points per second now. So as the year go by, every manufacturer try to outdo each other a little bit, by a little bit. So here we have some photos of a scanner. You can see one is stationary there. So that's the configuration, the first one being stationary. That's the top one to the left there. That's a Leica C10. Also there's terrestrial scanning. One spot, put on the scanner, it scans, move to a next location, put on the scanner, it scans. The other one, you see a vehicle moving in a tunnel, and they have probably more than one sensor on it. And that is driving through there and it's scanning, so it's called it mobile. You have aerial now, where you have sensors are mounted on airplanes, and as they fly back, you have a GPS on the ground, you have corrections taking place, you have an IMU on board, right? And you can actually scan from the air, and it's called aerial type scanning, better known as LiDAR for most people now. And then they have these new handheld devices that could fit into small spaces where laser scanners cannot fit, and you could do scanning with these smaller type devices. Right? Some of these devices probably could even be used by dentists when it is they want to map your mouth, right? For dentists and stuff like that. So the scanner measures angles in the horizontal and vertical plane, and it also takes a distance to get an XYZ coordinate, right? The intensity of the return is also recorded, and the resultant of a total scan is known as a point cloud. So on the left there, we have the Leica machine, and you can see in the horizontal plane, it will spin a full 360 degrees, and the vertical plane, it will go just about 270 degrees. And to the right is a resultant point cloud there. It's not a colored point cloud, it's probably one based on intensity, and you can see it's a bridge. So more than likely, this would have been a mobile type scanner being used, driving along the road. So because it's over the road, the intensity, the reflection right there over the road, it seems to be red. So it seems to be the strongest at that point. The data workflow though now, look at the data workflow. We have the capture, obviously the laser scanner, but we have other pieces of equipment that can be used to aid the process, like the photographs. So people sometimes may want their work coordinated to a special network, because when you use the laser scan, you put it on, the coordinate system is at 0, 0, 0 at the center of the lens. And when you move to another station, it's 0, 0, 0 all the time. Some people want this information transformed to their local coordinate system or to a national grid. And that is why you need the total station and other pieces of equipment to tie in those points for that transformation. You also have photos, which is now probably archaic, but they have some scanners that do not have an integrated camera in them. So after the person scans, they will then take a camera, mount it on the same tripod and take photos all around, and then bring those photos in the processing software to add color to the points. When we go across the data processing now, we see we have some processing which is filtering. So usually when you do laser scanning, you don't really stop traffic. So you may have people walking past, you see them, have vehicles passing, a bird may fly through. All that information is captured, right? And some data filter needs to take place at that point in time. So the first part of data processing is filtering. After which registration takes place. As I said before, every single setup that you have, the coordinate system starts at a new origin as 000. So registration is that process which by all these scans are placed in one homogeneous coordinate system. So all these scans are placed in relation to each other. It's like building up a puzzle now. And then colorization is whereby you add the color. In most modern total laser scanners, there is a built-in camera. So the process is automatic. Others, as I said before, need to work with a camera. And when you finish that process, the output is a point cloud. Now, some clients, all they want is a point cloud, and they will take the point cloud and measure stuff within the point cloud. They might do their own extraction. Some others want an actual mesh or DTM. That happens more than likely for topographic type surveys where people want to see the relief of the land. A mesh or DTM is what you'll probably produce for them. Some people just want vector information pull out, especially when it is you doing LiDAR type work or area type work, whereby buildings, you want to take the building, the footprint of the buildings and put them on a 2D plan. Vector information is extracted. And some others want an actual 3D model or solid of the actual real world. Now, the 3D model could have two aspects. It could be a primitive model, meaning that the model is dumb, as they say. You just click on it, it gives you dimensions. Or it could be intelligent, but when you click on it, you get attribute information about it. You might say this pipe is ASTME, whatever the code, you might say is carbon steel 150. You get information in the flange, a 2-inch flange, and information is added to it. Intelligence, I should say, is added to it. So some of these scanning considerations, you must have line of sight. This is not a magic trick. You can't scan behind a wall and expect information behind to appear. Line of sight is a must. Scan rates, for it to be considered laser scanning, should be almost 0.75 of a million to 2 million points per second. The operating temperatures in very hot conditions, it wouldn't affect us in Trinidad and Tobago, probably in deserts where temperatures probably reach around 40, 50 degrees. This scanner would not operate. And very cool temperatures in the minus, this scanner wouldn't operate because the lasers emitted. Weather conditions, we don't have any snow in Trinidad and Tobago, but rain and very dusty areas, we could actually see that in the data when we process it. The type of surface is very important. The texture or reflective it is, the angle of return is a big thing, especially when you're laser scanning around glass. So let's say you have a glass window, right? The laser scanner will go through the glass, hit whatever body behind and come back at you. In that case, that's not so bad. The problem exists is when it is you're at an angle to a glass and you get total internal refraction taking place, whereby the beam hits the glass, doesn't penetrate the glass, goes behind you, hit a solid object, comes back to the glass, and then enters the laser scanner. So then you get a much longer distance pointing at an angle. So what you get is that if a wall is behind you, this wall is now projected in the data in front of the scanner at twice the distance it is behind you. So that's a big, big thing in laser scanners in terms of windows and the issues that it could bring up. The battery life is usually around 4 hours. And in that time, you could do at least probably 20 scans, depending on what your scan rate set at. A typical high resolution scan is roughly around 10 minutes. As I said before, the ranging accuracy is generally between 1 to 2 millimeters, meaning that when you get a shot of a surface, that coordinate is accurate to 1 to 2 millimeters. And this is where some issues come in, because when people study the equipment, they say this thing is accurate to 1 to 2 millimeters. And people believe that when it is they do work on the pole dimensions in spatial space, you're going to get 1 to 2 millimeters accuracy. And that's not true. Because to measure an object, you must have at least measurements to the edges. So if it is I was to take a shot to the left of a chair and then to the right of a chair, and I have 1 millimeter accurate on one side and 1 millimeter accurate on the other side, the actual distance could actually be 2 to 4 millimeters accurate, the actual distance across, right? So that's important to remember. The overall accuracy of the project is inversely proportional to the number of scans, meaning that you have a lot of scans in the project, your accuracy sort of drop off, right? They call it scan drift. Now, there are techniques that can be employed to try and correct this. That's why this is a tool that surveyors for large projects should try to undertake, and not people who believe it's a simple thing to press a button, set some settings, and go ahead, right? Because I've seen projects where you have over 100 plus scans, and when the person reaches the end, they're out over, let's say, 200 millimeters, which is about 8 inches, and people saying, well, this technology not good. I always say it's 1 to 2 millimeter accurate, and all of a sudden we have a misclosure of about 200 millimeters, 100 scans later on, right? So there are surveying techniques that can be employed to try and control this error drift. And then we have software requirements on 8 gig RAMs. That's minimum. This is minimum requirements here. 8 gigs of RAM to run most of the software, a quad-core processor, a 4 gig graphic card, a solid state will be an asset. If not, if you have a hybrid drive, that probably could do also. The machine I have currently does not have a 4 gig graphic card. It has the minimum requirements. So I hope later on this stuff are going to show will actually run and don't really crash. So let's look at some of the applications we see inside of here. So to the first picture to the left, you've seen seems to be a model within a scene there. And I'm not too sure anybody can make out the other picture. That is the red house, which we'll speak about later on. To the right of that, you're seeing seems to be like a coastal area. And then you're seeing an area inundated with water. So this would have been an aerial type survey, LiDAR survey, and they would have been able to model the land or get a DTM of it. And then they could decide if it is a tsunami was to come in and we have the area inundated with about 5 meters of water or 3 meters of water, which areas would be affected. So that'd be good in public safety, that area. To the right of that, we have some looking like some flanges there, and that has to do with manufacturing. The one to the bottom left, down there, I think there's a pointer somewhere. Let me see if I get the pointer up. Right, this one to the left here is basically an as-built survey. As you can notice, there's a pipe here. There seems to be a bar T here, a bend. And you notice there's a green color in between the point cloud, and this has a blue color in between the point cloud. This is when you have modeled within the point cloud, and you see sometimes the point cloud hiding in front or going behind the actual solid. And that will happen from time to time, because when you do a modeling from a catalog, the assumption is that this thing is perfect. So you're going to get a perfect sphere, you're going to get a perfect cylinder, right? And that is being modeled against a point cloud. And that point cloud, obviously, we have issues, we say with the accuracy, we could have a 1 to 2 millimeter accuracy. And not only that, we may have deformation taking place on some of these vessels you see here. Because after, I don't know if it's something warm going through their warm product, you could have deformation taking place. So that is why it looks like that. You're seeing some green and sometimes not the green, and sometimes the blue, and sometimes there's the point cloud being shown there. So application laser scanning, and we're going to speak about BIM here now. And BIM is just really a process for creating and managing information on a construction project across the project life cycle. We'll be dealing with the BIM today because the BIM is the part which will tie in the construction, the evolving construction. And you see the words deal about architecture, engineering, and construction. And the oil and gas industry, everybody knows that AEC, you're going into type in AEC, you see these things come up, AEC. So the BIM basically addresses the AEC needs. So today we're talking generally about BIM and AEC. The application is 3D manufacturing. I showed you the little flanges just now there, whereby people do printing. They scan stuff and you can do 3D printing. Also have public safety, and this is catching on big in the United States. Besides the slide I showed you before where we had the area inundated with water. It could be used by the police. The police will go and scan scenes in the states and use it as evidence in the court, right? Also, they could scan areas. Let's say somebody was in a drive-by shooting, right, and have bullet holes in the door. They could actually go and scan the door, and then they could work out the trajectory of the bullets and where the possible shooter was, right? Even the fire department using laser scanning scenes after the fire to find the cause of the fire. Even insurance companies are looking at it because there are certain software that could try to recreate the accident by when you scan, you look at where the tire marks and skid marks are, right? And determining who was wrong and right in an accident. And then they have it also in entertainment, right? With VR, AR, I think it's Xbox Connect or one of them have some gizmo whereby it could scan you and you'll be in the game and that kind of stuff. So I have a lot more applications, but these are the 4 major applications that are leading to this right now. Right, so looking at this here, this is just a blob of the picture before, but in construction, topographic surveys, as-built, verification surveys. Engineering, we have reverse engineering, dimension checks, clash checks, simulation. And if you look, this is a dimension check, the one here with the circle here. Because what happened, a scan was done, and the scan is the grade area. And they wanted to probably install some more structural beams. And by putting it within the code, they realized there's a clash taking place here. So they have an option, one, to redesign it, probably make this higher to clear this little beam here, or they could decide to cut everything out fit to fit exactly there. So it saved them time and effort. Instead of going out into the field, going there, realizing there's an issue, you need to get a further, come and cut it. And then there's downtime. So out in front, they could plan ahead what could take place, or just do a redesign. Right? Architecture, if you look here, this is where we scan section of the Red House when it's under construction. For those who know Port of Spain, this is the Attorney General's office on this side. This is the Red House. And we did a few scans on the outside here. And this here is not a photo. This is an actual point cloud. The points are so densely grouped together, it looks like a photo. This is actually a 3D image in here of the point cloud. And there's a backdrop on this job, basically the Red House restoration project. Some of the walls, the columns, is an old structure. They wanted to reinforce it by using steel rods, right? Expensive steel rods, stainless steel rods. So they wanted the exact distance from the ring beam going all the way down to the ground floor, right? Because they're exposed, we had to actually scan floor by floor by floor by floor. And with any point cloud, we were able to pull the dimensions to give them the exact lengths to cut. That was the initial job. Then it turned out, okay, well, since we could do that, let's check verticality. So they want to check verticality of the walls. And of course, dimension extraction for other parts of the Red House. So you see how laser scanning in one breath needed one, they wanted one outcome, and now everybody jumped on it to get extra data out of it. In this one here, this is a floor here, and this is floor flatness, floor levelness. Right? And this basically, you could say like a topo map, or probably I would more say like a heat map, showing the elevation differences throughout the site. They have advanced software now that you could actually do an ASTM 1155 check, whereby you put your lines, and will give you the floor flatness and floor levelness numbers spit out for you from a laser scanner. So we did the laser scan here. The client wanted ASTM 1155 report. He just wanted to see where were the high and low spots within this area here. And this was, I think, one of the floors for the Point Fortin hospital that was recently commissioned. And of course, I mean, taking all these shots here traditionally would have probably taken, I would say, probably at least a week. This is a large area to cover. Right, with the laser scan, I mean, this probably would have been like about 2 days, probably even a day, depending on how traffic was when doing the survey. Right, and we spoke about these applications. We have the VR, we have the AR, virtual reality, augmented reality, and this is something not even in entertainment, even I believe I saw it in engineering works for mechanics, whereby a school had these AR goggles, put it on, and showed mechanics and train mechanics how to disassemble engines, and they were able to much faster with this aid. And of course, 3D printers is a big thing. There's a professor in the University of California, Professor Koshnevis, and he is working on something called contour crafting. It's really a disruptive technology. And he is actually looking to print buildings, right? So there's some videos online. If you go and just search contour crafting, and you would see the professor there out of California, and they could actually print a building for you in 2 days, right? It is not commercialized as yet, but when this goes on, this will revolutionize the construction industry, because he's talking about tensile strength for the walls about at least 10,000 PSI. And imagine you put up all these walls within a day. Also, the electrical components are automatically being installed. Everything is being done by robots. So I think he's a robotics specialist at University of California, right? So BIM, as I said before, it's a process for creating and managing information in a construction project across the life cycle of that project. So construction ills, and this is where this BIM ties in with laser scanning to try and solve some of these ills. The first thing is slow in many cases. Construction is slow. There are many projects, when they say going to finish by December, well, generally 8-9 months will pass. And it doesn't have to be government projects, it could be your own project home. To show people that issues, a builder come, you say, yeah, that will take 2 weeks, and realize 2 months he's still there. And there's always an excuse why something went wrong, they didn't expect this, that kind of stuff. Also, very hazardous jobs. In states, I think like almost 8,000 or 9,000 people a year die because of the construction, right? So it's a very hazardous job. And in some cases, laser scanning could be employed to avoid some HSSE issues. Wasteful at times. Many times people may order too much, right? They may do something, it's in the wrong position, there's a rework, right? And this is a next big issue with construction. Wasteful at times. I had a guy come by me sometime to do a ceiling, and he said, buy X amount of this, realize it's too much. I have about 3 or 4 pieces of material just wasted at the back of the house. Corruption prone due to many trades involved. And this is a big thing. Managing a huge construction project is difficult. You have a whole set of people, a whole set of trades involved. You have surveyors coming in the beginning, you have electrical engineers, you have mechanical engineers, you have civil engineers, you have the architect, then you have the carpenters, the masons, a whole host of stuff. And once these things are not managed properly, I mean, it could end up in corruption taking place later on, right? And in most cases, costly and over budgeted, right? So hopefully through laser scanning and BIM, a lot of these ills could be addressed, right? So just looking at the life cycle here, BIM, FARA is one of the manufacturers of laser scanners, and they gave me this nice little slide here. So we have this FARA slide. So you can see the 3 main phases. Of course, the design phase of any project, building time, operate time. Of course, there's a small arrow going out here saying demolition if you want to demolish, or you could continue by renovation or modification. So it comes like a life cycle. So we have these little icons here, and you can key at the bottom. This one represents a laser scanner, and it says on-site capture. The other one is as-built model and design, which is a software will do this. Design layout, software will do this. Quality control, right? Software again. Data connect and share, which is a big thing, software related again. If you look at the design, you have conceptual, detail, analytical, fabrication. If you look at all of those steps, the laser scanner is involved in all. Actually, for the entire life cycle here, the laser scanner is present in every single one, plus data connect and sharing, right? So it shows how important and integral the laser scanner is within the BIM for a project. So we're going to look at our project here. right, the sample project. This is a project, the backdrop, this is in PowerGen, and this is a cooling tower, right? To the right, there is the existing cooling tower. There are 3 cooling towers. This here, the cooling tower was demolished. So the client was interested in putting up a new cooling tower, and he wanted to make sure the fabricators of it in the United States had everything, all the measurements correct. One of the challenges was after removing the cooling tower, this pit here is about 2 meters in depth. So the scope really was to pick up the basin, pick up any adjacent piping that will tap in to the cooling tower tap into, pick up all the supports there, right? I think there was a building and a tank to capture. In this basin, there was a lot of slush, right? And moss. And there were over 100, I think over like 120 of these supports. And you had to take 4 shots to define the top of each support. So doing that traditionally meant that you'll have to pick up well over 500 data points, just alone for the supports. Plus, you get a ladder to climb up since the supports are approximately 2 meters high, and hold a spike prism or hold a mini prism on the corner of each of these supports. Also, because of the slush and the HSE issue, they'll have to get the next contractor to clean the area out, meaning that they take about 3 or 4 days to prepare the area, pay another contractor, and then go in with a ladder and climb up and down the ladder, right, for over 120 times, and hold the spike of mini prism on all these supports. With the laser scanner, this job was done like in about 1 hour, because I think only 4 setups were done at about 10 minutes each, right? And then it was processed, and then it was drawn up the next day. So you can see this laser scanner here, a big benefit. So I'm going to play the video here now, and we'll be going through the site here, and you can see the green lines there represent the vector extraction of the supports, right? If you look at the right-hand side here, you see the yellow a little bit. That is the actual solid model within the point cloud. It's coming in and out sometimes. When you see that, I mean the modeling is very close to the actual point cloud. We also took up some of the H-beams or I-beams here, model that, and actually base plate. And there was a wall on this side, and a tank, and a face of a building. Just want to know those dimensions. So all that was done within, I would say, a day. The scanning was done, as I say, an hour, processed for about an hour again, hour and a half, to process the data, clean it out, convert the data to the appropriate software to do the extraction, and then it took a day to model this section here. And this was really big time savings for them. This spot here where the circle is represents where the scanner was set up. So you usually don't get data over that point there. So I think 1 point was here, 1 point was on the opposite side, 1 point was here, or 1 point at the top here. So there was really about 4 points, 4 setup points. Okay, so, and this is the pipe that was modeled using the catalog. So this is an intelligent modeling. Once it is, you know the pipe specs. When you go into the catalog, you look for the pipe specs, and you can actually model along the pipe. Right? This other one here now is a crash detection at Heritage Block Station. And I have this data loaded behind the computer. So this is one of the files we'll look at later on. So what happened is that model in between there you're seeing, that model is the bridge. So we had offshore block station and a platform, and the original bridge was demolished. And they wanted to put a new bridge in. So they want to know where all the interfaces would take place for logistics to remove them. Right, and they also want to make sure, the first important, that the bridge was long enough to fit the span. Because they didn't want to go mobilize, carry crane, all sorts out there, and then realize, hey, this thing floating over the ocean is not connected. So what happened is that there were some interface points, all interface points where the bridge were. We surveyed that in manually with a total station. And then we linked it to the point cloud. So the point cloud, you can see through the point cloud here, and the kind of pink and the yellow and the brown is the actual proposed bridge. So I said, I have this data here, and we'll actually go through this data real time and try and run a clash detection test to see what the clash detection test would actually pick up. Okay. And the client from the report was able to determine what pieces of piping needed to be moved, and then able to plan logistics. We also gave them the output was an actual drawing, so they could actually see how the bridge looked in relation from a side view, which is important, because if the tilt is too much, it may pose a HSE risk where you kind of walking down a heavy slope and you probably could trip. Creates a tripping hazard because of the angle you're coming on at. And they were able to go ahead with this project and successfully put this bridge into operation. Right? See all the piping inside that need to be removed. So some of the results, which hard for most 3D people, is that when it is you do these type of jobs, 95% of the time you have to come back and give the person a 2D plan. Right? So you see here, we give the dimension of the bridge across, we give the angle it was at, we give the interface points at certain areas where you may have issues, where you may have clashes, and that was given to the client. So let me go across now to a spool piece verification, right? And in the BIM life cycle, this will fall under quality control, whereby a spool was built, and before going to install it, they want to make sure that the distances are correct and the angles are correct. We don't want to go transport this thing to a site and then realize, hey, it can't fit, it can't work, right? So they call us in and we did a laser scan of the spool pieces and then model it. So let me make sure the share audio is on. I think some of them may have some audio later on, right? We see the same life cycle there, spool verification. The 3 scans in 30 minutes. 10 minutes per scan. Then point clouds, bring them in. From that, start modeling, see that green line, red, pinkish line coming as the modeling takes place in between. Those were the points along that we chose for fitting the actual pipe within the wall. But generally, this traditional means would have taken a little while to do it. I'd have probably taken this part over day, half a day, to take up one shot to put the one of the pipe, but it is kind of 2.5 hours. Within an hour, it was modeled. Okay, we'll go to this other video though, before we start going into data interrogation now. This is a FAR video that shows some of the products they have. It will show us about the different types of configurations we spoke about earlier, which would be the terrestrial, the aerial, the mobile, and then after they go into an actual live construction site, and the guy there would explain what the advantages was using the actual Faro laser scanner. So I hope you all hear any audio. If you're not hearing the audio, probably you could just leave, because the audio is important in this one. Just now, let me go back. panel there. You can put it on the tablet and mobile setup panel. You can put it panel drone.
Smith with Faro Technologies. I'm a senior laser scanner account manager here today with Mike Rizzo, the BIM manager with PCL Construction, on site at the new City Tower construction project that you see behind us. But Mike, earlier today you were telling me as we were walking down here some of the benefits of utilizing the Faro laser scanner that you and PCL saw early on in the build out of this project.
Yeah, actually, the first thing we did out here on our project is we came down here, did a full laser scan of all the surrounding streets so we could have an accurate as-built of everything that we're dealing with. Then we took that scan and we dropped the BIM model right onto it in the exact spot where it's going to go so we could see if we had any conflicts we didn't anticipate. And we actually had one right here behind me where there was a telephone pole with some electrical lines on it that ended up being too close to the building that we wouldn't have noticed if we hadn't dropped the model onto that scan. So we knew that we had to make some adjustments, put an outrigger on one of the lines to push it away from the building. So it actually helped us in safety and helped us in scheduling and planning. It's something we wouldn't have noticed if we hadn't had the scanner.
Excellent. Thanks for sharing that. Well, now we're going to head up to the 8th floor here and show you some inside scoop on the new Faro S350 laser scanner and show you other ways that Mike's team here is benefiting from utilizing the Faro laser scanner solution. So here we are now on the 8th floor of the City Tower. Just want to show you the contents of the backpack that we brought containing our Faro S350 laser scanner. So inside the backpack contains our Faro S350 laser scanner head unit, as well as 2 lithium-ion batteries, any sort of charging cables that you may have. This entire backpack setup, including the lightweight carbon fiber tripod, only weighs 19 pounds. So any man or woman can easily climb ladders or move throughout a job site very easily. One of the most obvious upgrades to the new Faro Focus S350 is this larger and luminous touchscreen display. So here the operator has full ease of use of adjusting any sort of filters or parameters or file structure inside of the laser scanner itself. This luminous display also has the ability to adjust between a dark and bright feature to make it easier to see out in direct sunlight. Although this device may look very similar to our older S120 and our X series laser scanners, this is an entire rebuild from top to bottom. So this is our first fully enclosed laser scanner head unit. So as you can see, the lithium-ion battery and the SD card are built inside of the head unit itself. And what that allows us to do is this is our first Ingress protected or IP54 rated to protect this device against moisture and dust. As well as we also have extended the temperature rating of this device to as low as -4 degrees Fahrenheit and as high as 131 degrees Fahrenheit. Because a lot of these devices are making their way into very hostile territory. For more information about the practical applications of the Faro laser scanner and our end-to-end scene workflow solutions, I'd like to bring back Mike Rizzo, BIM manager with PCL Construction. Hey, Mike.
Hey, Sean.
Can you tell us a little bit more about how you guys are benefiting from our Faro laser scanner and the scene and some of the apps you guys are using on this City Tower build-out?
Yes. In addition to the pre-pour scans, we also do post-pour scans of every one of our slabs. And then that way we're able to take those scans, bring them into scene, register them, then run the Rhythm Builder and Inspector apps on top of that, which will give us accurate heat maps as well as floor flatness and floor levelness reports, which eliminate the need for bringing out a separate inspection team to do the dipstick readings. We can do it all within scene. We have all of the historical data from every slab.
So that's a huge time savings.
Oh yeah.
Well, thank you very much, Mike. I really appreciate it. Good luck with the final.
All right, thank you.
For more information on the exciting new Faro-focused S350 laser scanner, or if you'd like an on-site demonstration of this new device and our overall end-to-end software solutions for you and your organization, please visit us online at aec.faro.com, or you can contact us at 1-800-736-0234. See you soon.
Okay, so in that video, you see the advantage of using the scanner, whereby there's a known piece of equipment they use to do the floor flatness and floor level. It's called a dipstick. And they just eliminated that by the use of using the laser scanner there. And they also realized there would be a clash detection that was noted after scanning the surrounding area and dropping the actual proposed model within where the area is supposed to fall. So we're going to go into the data interrogation. I'll go into 2 more slides, and then we will go into some live data I have on the machine, and then we'll close off and go into any kind of questions. So basically, the work scene for what we use the Faro scene to register all our work. So we have the Faro scene, and that is the registration software. That's the software that puts all the scans together into one homogeneous point cloud. So you'll accept raw point cloud data from the FLS scanner, right? Not only that, it will also accept E57 information, right? Now, E57 is a special format, a format that was created by ASTM, which is formerly known as the American Society of Testing Materials. They have a code called E57. There's a committee, I should say, the E57 committee was created in 2006, right? It meets twice a year to deal with 3 imaging systems. And I really care about it because everybody was doing its own thing, and they had the population at large at a stranglehold, because when it is you go and buy a Faro scanner, you have the FLS files. They will have specialized software to deal with FLS alone. If somebody buys a Leica, they have the PTX or the PTS, they'll have Cyclone and other specialized software. So what happened now is, let's say an operator, I know BP decides they want to do a job, it is a scanner, we do FLS files, and then later on, somebody else comes with a Leica scanner, and the system cannot integrate 2 data sets, and there were issues, so they're stuck with this one provider all the time. So they saw that issue, and they decided, hey, everybody must have an E57 format, an equivalent to the drawing world where you have MicroStation, which is .dgn, you have Autodesk, which is .dwg. There's a DXF file, that DXF exchange file that you could use to exchange between the different software. The same thing here, that E57 is that equivalent to a DXF, right? So the Faro scene will import the data, you could process, edit information, and register the points, color the points, you can manage data in there, and you can convert to some other formats. So you must be able to convert to the E57. So all the newer software, probably from, I would say, 2010 onwards, they must have that convert to E57 format. Scene Light, though, is a free video that allows you, if somebody is to give you a Faro scene file, you'll be able to actually open up that FLS file in that free viewer and look at all the images. Because on top of having a point cloud, you actually get images that were taken, which is very critical sometimes when people do modeling. Now, Autodesk has a software called Recap, which is now actually extracting those embedded images within the FLS and other providers of laser scanners. So we swear Recap. So we have Recap here, not Asterisk is the Recap Pro. So you can do seamless viewing of billions of points. A lot of software, after a while, you put 20, 30 scans, you start looking at a data size, generally a high resolution scan would run you about 250 megabytes, right? So you have 10 scans looking at over 2 gigs, right? You have 100 scans looking at over 20 gigs of memory RAM you need on your machine, right? But Autodesk Recap is one of those software that can take billions, or probably limitless amount of points within the system and still be able to view and go through it. Right, you could also edit point clouds, you could extract some dimensions, so if you can't do any sort of modeling, you could also do some format changing inside of it. You can export to E57 also. But it's an excellent tool, people. You'll be using more for QC and viewing. So if it is you have a lot of points, a lot of scans, and we don't want to go through going through all these scans because you're going to slow the machine down, put it in Recap, and we can go through Recap, and go through the points more seamlessly. The asterisk there is that Recap Pro now registers data. For some people, some providers like Surfacer. Surfacer is probably the best laser scanner in the world, but they don't really do a lot of promoting because they more for the air industry, airspace industry. Their scanners are very expensive, 100,000 plus for their scanners. Generally, a high resolution scanner now runs between probably 60, 70,000 US, right? But they will probably hit you $120,000 for a Surfacer scanner because their scanners hit you 1 millimeter accuracy all the time. And most important is that the measurement angles is down to 1 second, meaning think of a 1 second total station, but a laser scanner doing it. So that's probably one of the few laser scanners, probably the only laser scanner that could give you that level of accuracy. But they do a lot of marketing, and they just go in the air industry and they scan very high resolution stuff. They do have a color option on their scanners. Data is so dense, they just use some other software if they want to look at color. But generally, the registration, they don't have any software registration, so you have to use like Recap to register their data or next third-party person. So they just deal strictly with scanning. Bentley Point 2 is the next powerful one, and Navisworks from Autodesk, which is catching on big time because Navisworks has that BIM aspect of it, which we'll look at later on, right? Because, you know, within the BIM model, you have 2D, 3D, 4D, 5D, going all the way to 7D. So, of course, the 2D is the third dimension, the Z component. 2D was just we have flat plan. 3D is when you add the Z component. 4D is when you add time to the data, right? So you can add time lapse or for scheduling. And 5D is when actually when you start looking at costs involved in it, right? So the Bentley Point 2 and Navisworks are similar to do a lot of animation, do clash detections, data overlay. Bentley Point 2 is very, very good at doing some clash detections that are mind-blowing. Most clash detections are static clash detections, meaning that you have, let's say, a point cloud, and you want to put something like a model into the scene to see what interacts. But Bentley even does dynamic clashes, whereby you may have something on a conveyor belt moving, and you have a solid somewhere, and that is moving also, and it's actually working out those dynamic clashes, which will move along a path. Okay, so let me go now and see if I can change my screen to one of the let me see for it here. All right, I think I've seen it here now. Right, so this is supposed to look slightly familiar. This would have been a job with the bridge I spoke about earlier on with Heritage. So this is point clouds. And this is just really 3 setups on one side here and 4 setups on the other side here, right? So let's just kind of go in closer and you see the data will start to reach in as we go in. All right, so 3 setups were done on this side. Okay, you see somebody in the scene here. On the opposite side, looking around, 4 setups were done on the opposite side here, right? 4 setups were done on this side. Mind you, the face of this block station here was picked up from the opposite side. So when you set up on this side here, this face was picked up, and vice versa. When we set up on this side, this face on this side was picked up. So the first thing they checked was to see if the distance was such that the actual model or the actual bridge that was built would fit in between. So let me put all new model inside of there. Right. So that is the model inside of there. So you can see the bridge. Let's get a little bit here. Hope this doesn't crash. So I'm going to try and go on top of the bridge there and come down. And you can see they have some lines, maybe communication type lines across there, right? We have some piping, obviously, that will have to be removed. So the first thing they wanted to find out, obviously, if the distance there, the bridge will fit. On inspection, just visually, it looks as though everything is okay. Bridge should fit. Of course, these two legs at the bottom there, we found that, as I said, we surveyed the original cutout points, we checked the distance, and it was good. So within this point cloud here, we place that. The client wanted to find after what we need to be removed for us to install this bridge. Now, obviously, the stuff in the center here, they know for sure have to go. They'll have overhang on top and below, but then at the sides, how far out with any of these things obstruct construction? So there's something called a clash detection wizard, which you try to run now, if it doesn't crash. So I go to the clash detective here, and in the clash detective, you see we have the RCS files, and those RCS files are basically the recap files, and those are the point clouds. And the DWG is the actual drawing, which is the actual model. So what you do, you will say add test. I'm going to add a new test, right? We will call this test UTT. And then we're going to click on this RCS. We're going to click, we'll take off this one. We're going to click on that RCS and all these other RCSs, right? Point data, yes, right? On this side, this means a solid or block surface. Our tolerance of 0.02, which is 2 centimeters, meaning that, okay, this is a clearance test. So anything within 2 centimeters of the actual model, we will call it a clash, right? The pure clash detections, it must intersect. But in this case, we're giving it 2 centimeters. We probably could give it a larger number, but the larger the number is the wider the search engine will be and the longer the clash may run, right? So in reality, if somebody needs to put in a new bridge, they might say, okay, we have this on a crane. It's possible with what we have on the ocean. Anything within a meter might cause a challenge. So we may have to clear stuff out there, a meter, clear of this, right? So we should put a meter in here, but putting a meter here would probably let this run probably 10, 15 minutes, which I don't want. So I'm gonna put it at 2 centimeters. So on that side, we have the laser scans. And on this side, we have the drawing. All right, I'm gonna hit run test. Run test, and you see it's working. It's finding clashes, 35, 41, it's going up the road. It's found 53 clashes, and it's now at about 30%. So it's about 50% now, and 67 clashes already. If it is you wanted clashes that only intersected, you're probably putting tolerance exactly at 0 meters. So it's almost finished. It's just about 90% now. So we have a whopping, so 170 something clashes, and the first clash shows up there. So they show the point cloud and they show the actual model where the intersection takes place as a clash for you. And you can click through the drop-down menu and go to all the other clashes. It will actually just cycle out it. So let's go down. There's a lot of clashes in here. So let's probably just go down to clash. Let's say 107 and click on it. Realize clash 107 seems to be part of the grating. It's intersecting with something there. So you could actually go across on this side here and try to go to see exactly where that clashes, where the point is actually intersecting with it. And you can see here, it's an area there where the points are coming out in there, and that is a clash there. So know for sure that will have to be removed, right? You could try and choose another clash area here, clash 108, right? There's a piece there. Let's look at it. It's there. Now, in this case, it looks as though it's very close. It may not be an actual intersection, but that distance there may satisfy the 2 centimeter spacing, looking from top view, right? And so forth. So engineers would use this program to go through for clashes inside of Navisworks here. All right. Probably just look at one more before going to the last one, the next clearance test. This seems to be more the outside here of the actual bridge itself. All right. So let me close this one off here now to release some memory from the computer. And we will open up the last data interrogation one. Okay, so here we have project here. I have some lines in between. So this project was a very nice project. It's not my project. It's a very nice project whereby they usually full BIM inside of it. They actually went to 4D, which is the time. So if you notice, there's a word simulate here. And what you could do with this, you could actually take your Microsoft project folders or files. So you go in Microsoft projects, you start a task. First thing is probably go and get legal papers. You do that, you do everything, the whole life cycle, the whole project inside of there, you place inside of there with your timelines. And you could bring that Microsoft project file into here. Once you bring that file into here now, everything that's a component, everything that is a component, you could actually now tie it in to your Microsoft project and then play it back over a time lapse. So I'm going to hit play here and you're going to see it's simulating and the days and weeks are changing on top of here. And you can see stuff is taking place. Piles are being, all those white lines are piles. And you can see the building is forming over a period. So it's still building, it's building again. You reach day 600, day 700, and I think it ends at day 800 and something. So day 837, week 120. So you see this whole time lapse here. So let's go in here. And what is good about it, this is also intelligent. So if I was to click on one of these items here, it will come up saying pile, right? And go to the hierarchy, that's a square pile there. If I go right above it, it says pile cap. Go to this box here, pull box with some sizes. Come across here, it says white flange. Let me just try and minimize it in here. So that's a W10 by 68, right? So of course, I mean, that's the white flange, is about 10 inches and 68 pounds per foot is the weight of this actual beam. If I was to click on the actual beam, all will light up that belong to that group. If I was to click 10 by 77, all the beams in front would light up, right? Let me come inside of here now. And I'm seeing like a kitchen here. And this was done so nicely. Even the components, I click on this here, comes up. It says Turbo Chef, Combi Oven. Come back this way, click Assembly Tray, right? Everything is nicely cataloged. Come across here, there's some dispenser or some, click on that. Yeah, beverage dispenser. So let's go to somebody more components. I like to see valves. I love to see valves. You can see some valves here. So let me turn around here. Inside the ceiling apparently. Right, I've seen some valves here. Right. Click on this, comes up. Right, 2-inch ball valve. If I click on the 2-inch, yeah, our next 2-inch ball valve is there. Click on this one here, 3/4-inch ball valve. So everything gets cataloged properly. There'll be some red stuff. I click on this, what it says. light and switch. Right, so every click on that foundation came up this foundation slab. So everything here has been properly cataloged, differentiated, classified in this project. And what they could do, they could also add the costing component later on. But for now, what they have really is just a nice model that's intelligent, and it has the time lapse inside of there. So somebody could decide, hey, on week 100, where are we supposed to be at? What's supposed to be built at around week 100, right? So I'm reversing it. You see the weeks are going back here, going back, and things are coming off. I'm zoomed in. So you see stuff, I'm gonna pause it there. So around week 67, this piping should be coming in inside of there, right? And people could actually go and look at down there what's taking place, electric, duct bank, concrete pavement, things like that. And you have the Gantt chart at the side there, right? So play it back one more time again. Let me zoom out again. So you see it's building the piles, pile caps, going up with the foundation, the structural work, flooring, piping, plumbing, electricals, everything. I mean, this takes a lot of time to put together, but when you do it, I mean, it's phenomenal. And this is where managing of the human resources and what could be done, because once you have this on the critical part within your Microsoft projects, and you have contingencies on the critical part, you try to make sure that your project doesn't go over. There are some items that will not affect the overall completion date, but items on the critical part are very important. This is on the roof. And this is the piping. Click on it, it might tell you what it is. This is solar heater. Yes, solar water heater, right? So the person put a lot of work and effort in putting all this together here, right? So let us go back to the presentation now. All right, so after the data interrogation, right? We have some point cloud analysis software. Build IT is one of them. I didn't show Build IT, and that is a big one for BIM. It validates the BIM, meaning that that nice little model we saw this now, you scan it, or scan sections of it while doing construction, and you put it within the BIM, within the model, and it would tell you if these components were placed in the correct position. It could also work out tolerance evaluation. So let's say you have some beams that are slightly bent or warped or not plumb, it will show up. And then you have a monitoring exercise also in there whereby you could actually monitor progress of a building, or even if you have earthworks whereby something happened, you can monitor movements and you can show it. The modern software we use basically is the PointSense Pro, now called Faro As-Built or VirtuServe. And people who work basically like they more use the Cyclone CADWorks system. ClearEdge 3D is an automated software that pulls out a lot of 3D extraction for you, right? Or it pulls it out, it will be intelligent because now you need to tell the shape exactly what you are, right? But because of the Exchange E57 format and the open up of the market, most of these software now are scanner independent. They will take most of the major type scanners, which will be the Leicas, the Faros, Topcons, the Regals, the ZNF scanners, Surfacer scanner, and those are the major scanners. I think Trimble has a scanner also, right? But in the beginning, Trimble was actually using a Faro scanner, right? In the beginning, I'm not too sure. I think it looks as though they're using a ZNF scanner now. Come down to the end here. So the benefits are quite clear, and the benefits basically will address some of the shortcomings or the ills within construction, which is number one, improve delivery time. Because you have all this data, we can move faster. We can make decisions at a faster rate. Elimination of rework, which looks at wastage, we spoke about earlier on. People do something in the wrong position, they'll break it down, they'll cast it over. Right, it will deal with elimination of rework. Huge data pool, which is a big thing. So before you have all this information, many people from different facets can look at information and share. Not only the mechanical engineer, but the electrical engineer, the civil engineer, everybody could use the data because the data is 360 and it's all around. HSSE, reduced risk. Because it's non-contact and no one has to go on a scaffolding or work up on an edge to capture information, people don't need to go in dangerous spots for us to capture the information. And next thing is offsite inspection because of the COVID. Great. All the data can be shared online and engineers can log in on our portal, right? Most of the time it's some online portal and they could view the data, they could pull the distances, they could check the progress of the project without actually going there. A lot of project managers do that, especially if the project is a foreign investor. He wants to probably look at what's taking place week by week. Scans could be done and uploaded, and they could be looking at the progress of their project. And of course, visualization and simulation is another big thing, whereby sometimes you want to install something, you don't know how it will look, how the logistics will run. That will basically help out in that. And all of that together just basically comes in savings and costs for you in a project. So it clearly shows you this kind of truly the BIM life cycle, right, is a very good tool to have, right? Because it will really assist you in your day-to-day projects. And that's it there. So thanks for your time. I'm not too sure if anybody have any questions, if they were bored, if people sleeping. So back to you, Ms. Padisi.
Thanks so much, Mr. Grant. So I'm seeing in the chat that we have a couple of questions. So Brian asked, are there developments on this tool which are AI oriented, and will it eventually reach there?
All right. Now, in terms of the artificial intelligence, it hasn't reached there as yet. What people looking at for most, how to put it, engineers, they're looking at an automated way in which you don't have to manually go and model stuff. They're looking at you put on a scan, and later on, boom, you see everything cataloged, wood, metal, and in time, probably based on the returns they get, and they may be able to try and classify information and materials and stuff from the laser scanner. But in terms of artificial intelligence, meaning somebody like a robot running it, it is very possible. Probably a robot could probably have a scanner installed and the robot is actually just moving along, scanning. So no one has actually come up with the idea to build it as yet. It's still man-driven. Man goes out and he looks for the best locations. And one of the issues really is for large projects. For smaller projects, I think a robot or something may be able to go through and scan. But for large projects, you need to have some level of survey control placed in there to tie the survey in so that it doesn't lose its accuracy lower down the road. But that's a good suggestion. And I know there are a lot of people trying to develop this, whereby it just be like a black button something, and the whole world wants to go to this AI thing whereby not much human intervention involved.
Yeah. Okay. DeMarcus asked, with the advancement of this technology, will there be any use for structural engineers? With respect to the video where the guy said that the software costs them lesser than hiring inspectors.
Right. Now that's a big thing. Not only that, even surveyors, because this software, the hardware is so easy to use. You press a button, you capture the data. People ask, well, we don't need a survey to come out. We just need a technician to capture the data. Now, for that aspect whereby you spoke about civil engineers, you must need civil engineers, right? Technicians that went out to capture the floor flatness, floor level, they may be sidetracked. Tell you honest truth, with technology, there's usually some level of casualties. So before you have a technician coming out with a dipstick to do that measurement, but all it means is just retraining, because there was it may involve now the contractor now getting the same guy who did the dipstick readings to be trained in use of a laser scanner. So if people could see it as a way of developing this stuff into some other function. So I mean, yes, the actual inspector coming out to do that, he may do something else, but he can get the opportunity to learn how to use a scanner and to do simple scans, because to do 1 or 2 scans, anybody could do it. You don't have to be a surveyor to do it. Surveyors are for larger type projects where you need to combine total stations to get a tight point cloud. But for some smaller areas where you have 1 or 2 or 3 scans, I mean, most people could be trained to do that. And I don't see any reason why it is the inspector can't be trained to use the laser scanner.
Okay. All right. So I'm seeing Ivan asked, how much time was spent in planning for the 1-hour scan highlighted, and what was the most significant human error risk identified?
When I say the 1-hour scan, that was the scan with the cooling tower, I believe. I believe so. I think I said the cooling tower.
Yes, the cooling
tower.
Yeah,
the cooling tower, right. So that area was pretty open. So we didn't have much challenges. Challenges take place when you have cluttered areas and we're trying to distribute the targets evenly. Because to get a good accuracy, you should have to have the targets spread out like 360 degrees around you. In some cases, if you're moving and you only have, or let's say moving along a shore, you can't put targets on the seaside, only on one side, and that becomes a challenge. So the biggest challenge really there was just getting permits. There was no challenge. I was open. It was fine. We only did 4 setups. The only challenge would be probably in the modeling aspect. If you want to talk about the challenge, data capture was fine. When modeling we didn't do any modeling today, but when modeling the top of the supports, some of them were chipped, right? So we had to use a software within the modeling there that will allow us to analyze a surface. So basically we analyzed the 4 surfaces, and the 5th surface was the top surface, and then ran an intersection on it. So it intersected all the surfaces and created the true corners that were chipped off. So that was the biggest challenge, because when you click on the surface, it would tell you, okay, this plane, you've clicked 20 points, but 3 of the points are probably 8 or 6 mils out, and we could delete those points and fine tune until we get a plane that's probably within a millimeter or 2 accurate, and then go about that. So the biggest challenge was in the modeling. That data capture really is because we didn't have to move these spheres, because we have some targets that we go with. So sometimes you move the targets when you travel in, but the targets stayed one spot, and we just move the instrument to 4 locations. So that was a very easy one. So the biggest challenge was actually modeling component for that 1-hour job.
Okay. So I'm seeing we have the Marcus asked again, with the 3D model, the smart one, which gives you all the information with respect to the different standards and units, imperial and metric, is there a specific software that deals with that, or do you have to configure it based on what work you're doing?
Okay. Well, believe it or not, for some reason, I mean, all the surveys are done generally in metric. But we have this issue with the American standard, especially for piping. We still say a 2-inch pipe or 4-inch pipe, but when you list it, it's in metric, right? So all the catalogs generally will come in imperial, right? So when you're catalog driven, you're driven by that catalog. Now, in software we have a metric catalog and an imperial catalog. So we just choose which catalog we're going to use. But we always measure in imperial because we are custom with the metric system. But the software will easily switch in between, because although we're measuring in metric, I will say I want my catalog in imperial. I will actually extract and say, okay, this is a 6-inch diameter pipe. When real life it measures 150 millimeters across, which is 6 inches. So the software is smart enough. You just tell what you want to work in, and it will display that in the catalog. Because as I say, everybody still say a 6-inch pipe, a 5-inch pipe, 4 by whatever inches, you still go in the hardware. And a man say you want a 2x4. You don't see you want a 5 centimeters by 10 centimeters. That kind of thing. Yeah.
Very true. So Andrea asked, where is the largest area conducted laser scanning in Trinidad?
When you say laser scan, you mean terrestrial laser scanning, or I'm assuming terrestrial we're going to speak about now. Now, in terrestrial laser scanning, the largest area I ever done would have been a facility, a BPTT facility, a gas facility, which probably measured about 150 meters by about 200 meters by about 80 meters across, right? That's the slug catcher in Beachfield. I think the largest I know of would have been somebody has scanned the entire BPTT facility in Galeota Point, and that's the biggest terrestrial laser scanner I know of in Trinidad and Tobago. I know abroad people have done scans where they had over 1,000 scans in the project.
Wow, okay. So we have another question here. With respect to storage of the point clouds, what would you recommend for an organization now starting to use this technology?
Okay, that's a really good question. Now, a lot of people fight up with that. Initially, we have a server here and we used to store stuff on the server. After 10, 15 projects, we realized, well, we don't have any more space. People start storing these stuff on these backup drives, the external 1 terabyte backup drives. But now people are more moving to the cloud. So there was one of these slides which speak about connect and share. So a lot of the suppliers now give you web share options whereby you pay a subscription fee and they will host your data and give your clients passwords, or you could give your client passwords to log on and they can view their data online. So everybody going to the cloud because it's much easier, because after a while people have, sometimes we had at a point now about 20 of those little 1 terabyte drives pack up in the office in a drawer, and when somebody looking for a file, the search issue to see which one to use to pull it down, because some jobs could get huge. As I said, one job, which was one of the BPTT jobs where we scanned the facility, it was about 180-ish scans, right? Sometimes when you convert these scans, they want another format, and then to model, you pull to another format. That job easily ate up 0.5 terabyte, right? So think about you having jobs like that, people going to the cloud. But generally, if you have a good server and you could probably host it on a server and still back it up on some drives, because some clients would tell you, yes, we get the job, but we want you to hold this data for us for 3 years. So after 3 years, we just delete it and move on. So that's just really it. But store it on a hard drive or computer is a risky thing. Backing it up on a server, backing it up, and having that server backup is also important.
Okay. Well, I think that is it for the questions. So just to give everyone a heads up, this talk was recorded and will be posted on all our social media platforms. But before we sign off, I would like to please share my screen. Right. So on behalf of the chapter, we wish to thank you, Mr. Grant, for taking the time to facilitate this talk and enlightening the UTT SPE community and industry personnel on laser scanning in evolving construction. So thank you so much. This will be emailed to you.
Okay, thank you very much, Ms. Padisi.
So thanks everyone for joining in today. Take care and have a great night.
Okay, take care.
Same to you.